Hi everybody, what we're going to be doing in this video is having a last little look at forces, specifically to look at over the merit and the distinction criteria that really look at the application of forces. So what we're going to do is going to kind of work through 7 key kind of areas that are going to really push you towards getting these merit and distinctions attacked. So I'm just going to share my screen. And we're going to present from here. Okay, so just let that load. So what we're going to be doing is looking all about forces, essentially. So we're going to have a quick look through as we said, the applications of forces in the world around us. So a lot of this is going to focus on kind of our space travel. It's going to look at things like parachutes, and we're going to have a look at Formula One in the use of forces in Formula One, and to really help you to understand these merit distinction criteria. To start with, though, what we're going to be doing is talking about the old master. Okay, so the old master being this guy, Isaac Newton. Okay, and you may have seen this. May the mass times acceleration be with you before. Okay, and you might wonder, what the hell does that mean? Now, what we need to be comfortable with is that Newton essentially stated that the acceleration of an object is directly related to the net force and inversely related to its mass. Now, what does that actually mean? If we actually break this down, what this actually tells us is the acceleration of an object, how fast an object goes from one speed to another speed. It depends on 2 things. Firstly, that's the force behind it, and secondly, the mass of that object. So a small force acting on a really big mass isn't going to accelerate it very much at all. Newton basically acted to quantify this in the form of a formula. Okay, so and we know this as force is equal to mass times acceleration. So that is what that actually means. It's a bit of a nerdy joke, yeah. We love it. So we love a bit of a nerdy joke. May the force be with you, indeed. So mass times acceleration is what we're actually using there to calculate the force, and we're going to be using that in the assignment to make sure that we understand how forces and this understanding is applied. Now, what about the apple? That's the first question that comes to mind for me. You know, we're talking about Newton. What did he actually, what did he discover? And there's this kind of story around the fact that, Newton sat under a tree and the apple fell and landed on his head. And he had a brainwave where he thought, why does that happen all the time? It's not strictly true. He didn't necessarily sit under an apple tree, but some of those ideas may have come from watching apples fall vertically down every time. They always fell downwards vertically, not to the side, not slightly diagonally. It was always directly down. And there's a pattern in that. And what he started to think about was, why is that? So in 1687, he published his law of universal gravitation. And this stated that every body, and what I mean, not by everybody, not everybody, like what I mean by that, what I meant by that was a body is a thing with mass. So everything with mass in the universe is attracted to every other thing with mass, with a force that's proportional to the mass and inversely proportional to the distance between them. Okay, and what that actually means is that right now everything around you is pulling you towards it, and you're pulling everything towards you. But the thing is that force is extremely small. So the things that aren't flying towards you, thankfully, what we need is a really, really big object in order to get that gravity to actually mean something. If you think about the biggest object closest to you, is actually the Earth itself. So the Earth that you're stood on, the planet, and that overrides all gravity. Okay, so the biggest force of gravity that we experience as human beings is the Earth's gravity that keeps us on the ground. Okay, and that's what pulls that that apple downwards directly every time. Now, gravity, and what I mean by this is not the awful film with Sandra Bullock. What we mean is gravity is a force, an invisible force. You can't see gravity. We know it exists because if we take something like a pen and we drop it, it drops downwards every time. And we know that the Earth's gravity is what keeps us on the ground, and it makes things fall towards the Earth. Now, the other thing to note is that gravity gives things weight. Okay, so if you have mass and you're in gravity, then you have a weight. Now, when we stand on scales, what that actually means is we're taking our force. We're measuring a force there. That's the downward force that you apply to those scales. Okay. You always have a mass as long as you've got atoms in your body. So mass is the physical matter that makes you up. It's the atoms, whereas weight is the effect of gravity pulling down on that mass. This is important because what you're going to do in the assignment is going to start to think about the impact of different sized planets on gravity. Okay, so we're going to have a look at this here. So walking on the moon is one example of where we really needed to understand the effect of gravity and the forces acting upon the astronauts that did walk on the moon. Now, the moon is smaller than the Earth. It's a lot smaller. So therefore, it has a smaller gravitational force. Okay. Now, on Earth, gravity pulls things down with an acceleration of 9.8 meters per second squared. Okay, so that's the rate at which an object will accelerate if you drop it. Okay, and you always feel that acceleration, although you don't notice it because you're firmly on the ground, so you cannot accelerate any further. On the moon, gravity has a much weaker force, and therefore you accelerate at about 1.6 meters per second squared. Now, watch this astronaut. Look at how easily he's able to push himself back up when he falls over. He almost hovers in the ground for a second. So this is actual footage taken from the moon during one of the moon landings. And you can see that he pushes himself up, lands on his knees, and just raises himself up. Now, if he was to do that on Earth, especially with the equipment he's wearing, he'd need to be really strong to do that. Now, he's probably quite strong, but look at how easy he makes that look. Now, the key reason for this is because if we take an average 75 kilogram person on the Earth, we can actually calculate their weight, their downwards force on Earth. And all we do to do that is we apply Newton's second law. Okay, so we know his mass, we know that person's mass, and we know the acceleration at which they're pulled down. So we know mass times acceleration. So we do 75 times 9.8, and it gives us 735 newtons. So that's the downward force that that person would apply, and you'd need to overcome that to jump. Okay. Now, 75 kilogram person on the moon, again, we just apply Newton's second law. We take his weight, or his mass, and we multiply his mass by gravity, or the acceleration due to gravity. And it shows us that the weight of the person on the moon is 120 newtons, much, much lighter in that sense. So that's why this astronaut is able to do this impressive little trick where he pushes down, jumps up so easily. Okay. Now, this in action, then we can simulate how high you can jump on the moon. Now, this obviously we don't do this. The astronauts didn't jump this high because they were wearing suits that weighed them down and deliberately weighed them down, so they didn't float off into space. If you jumped too high, you could just carry on going, and then you'd end up in deep space. This essentially is a free body diagram, and on the left it shows the astronaut on Earth with the 735 newtons of gravity. Now he just needs to overcome that, so 735 newtons is needed to jump. Okay, now on the moon you only need over 120 newtons to overcome that. Okay, so as you can see, the astronaut's able to jump much, much higher, and he's using his spring to do that, but this is obviously to simulate the effect of the moon if you were to jump on the moon. Okay, so that's the thing when we start to think about gravity and the force of gravity and the effect that it has, and when we start to land things on planets, this plays a big role. Now, when we go to space, we then need to return to Earth. Okay, so especially if we're sending humans, or some of the future space missions are looking to bring things back from Mars and things like that, we're going to need to return to Earth, and that means coming back into the atmosphere and then dropping a very long distance at speed. And you don't want to do that badly. Okay, so we use parachutes, as we know. We use parachutes to slow our descent, and then that means we don't splat into the ground. Okay, so it's generally it's not landing necessarily. What it is the landing that kills you, because you go from such a high speed to a low speed, and if you do that badly, you're going to go splat. Okay, so we want to avoid that. Okay, so parachutes essentially are designed to slow the free fall of an object towards Earth. Okay, and they make use of air resistance, which is another force. So we've already looked at gravity. Gravity is a downward force, as we know. It's always downwards in that sense. Parachutes make use of something called air resistance to decelerate an object's motion before landing. Okay, if you've ever walked into the wind, you'd have known what air resistance is, essentially. Okay, so that's where the air is pushing one way and you're pushing the other. That is air resistance, and you can get air resistance even in the air around you. So if you move your hand like that, you can feel the air resistance. It's very small amount of air resistance, but if you move faster, the faster you move, the more that air resistance has an impact. Now, what we understand is, and this is the way a parachute is designed, and you can put this into your assignment, is that flat, wide objects create a greater resistance force. Okay, so watch this simulation. Look at the way the paper falls really slowly compared to the rock in air. Okay, and that's because it's wide, it's flat, and it therefore creates a greater air resistance. It's because that air has got to go around that piece of paper to get to where it needs to be. And because of that, it's pushing back on that piece of paper as it falls. And that's what a parachute essentially does. So as we can see in this image here, it's interesting when you watch these videos of parachutes being opened. It almost looks like the parachute is going upwards. They're actually not. It's just the camera is continuing to move at speed, and they're just slowing down, and it just looks like they're moving away, but they're not. Okay, so unless there's an upward wind that lifts you up, generally speaking, that's not the case. Now, this graph, this relates back to the first assignment that we did, where we looked at the velocity of an object over time. Okay, so this just shows us basically this shows us an overall free fall from a height. Okay, so the first thing that begins to happen is an object begins to accelerate, and as it begins to accelerate, we can see that from the start pretty much up to this, what we call terminal velocity. Now, terminal velocity occurs when the downward weight due to gravity is balanced by the upward force of air resistance, and at that point you can't go any faster. Now at this point you're free falling, you're going to be needing to open your parachute at some point, so the parachute opens, and at this point, generally speaking, so there we are in free fall. All right, and then that's terminal velocity there. Well, not quite terminal velocity at that point, it's a bit further up, and there's your opening of your parachute at that point. And that just slows you down, and you can see this velocity time graph just drops immediately. It's a massive deceleration, and you hit a second terminal velocity, and that's generally the terminal velocity you need in order to hit the ground. And you can hit the ground at a fairly slow rate. You don't want to stop completely until you hit the ground, obviously. So there we go. Now, when we landed, I didn't have anything to do with it. NASA landed Perseverance on Mars recently, and they did this also with the previous Mars rovers. They can't use parachutes. Parachutes are no good on Mars because the air is too thin. So what they have to do instead is they have to use these landers, and these landers use rockets essentially. So they use rocket thrust to drop gradually that lander down onto the ground, and then that rocket thing will just take away. So parachutes won't cut it on Mars. Although gravity is less, the air resistance is even less on Mars. It's got such a thin atmosphere. So that's an interesting thing to consider. Now let's take a seat for a minute. Okay. That's worked quite well. It doesn't matter too much. The key thing that I've asked you guys in this next bit is to start to think about normal forces. Okay, so what I mean by normal forces is forces that act when objects interact. So the best interaction we can think of is when you sit on a chair. And the question I've asked you guys is, what stops us falling through the seat? Okay, and what I want you to think about here is, why do you stay on that seat? Now, I'm not talking about when a seat collapses underneath you, because that's just because maybe you're too heavy for that chair and it breaks. What I'm talking about is what stops things pushing through. So when you put something on a table, like a cup on a table, what stops it falling through the table? Now, the key here is it's all about atoms. Okay, so the atoms in the chair and the atoms in your bottom or your legs, whatever, have electrons going around them, and those electrons have a negative charge. Okay, and as you bring together a negative and a negative charge, what they actually do is they repel. Okay, they push away from each other, and that stops the atoms in one layer spreading and mixing with the atoms in the next layer, and those layers just sit on top of each other. Now, that repulsion is stronger and much greater than the attraction of the gravity between the Earth and you. And this basically creates the normal reaction force that we see generally. Anytime that something's on a surface and there's an upward force, it's going to be a normal reaction force. And it's always a normal because it's at 90 degrees from that surface. Okay, and that's quite important to note. Okay, so what we're going to do at this point is we're going to move into the world of Formula One, and we're going to start, rather than moving upwards and downwards, we're going to start to move backwards and forwards. So what we're looking at in this particular section is we're looking at the applied forces in a Formula One car. So what's doing that is an engine. Okay, so an engine that runs on some kind of fuel, probably a petrol-based fuel, that then drives a set of wheels that spin, and there's an applied force. That's key. So car engines are designed to apply maximum applied force to the wheels. Now, if we know a car's mass and its acceleration, we can apply Newton's second law to calculate the force required to move it. And you're asked to do this in your assignment. Okay, now I'm not going to give you the answers to the assignment because I want you to apply your own maths, but what I'm going to do is I'm going to take a simple car that weighs 1,000 kilograms. So it weighs about a ton. And it's going to accelerate at 5 meters per second squared. Okay, that's quite a slow acceleration compared to the cars that you'll see on a Formula One grid, but it's just an example. So what we need to be comfortable with is the force that is applied by the engine in this particular case is going to be equal to the mass of the car multiplied by its acceleration. So in this particular case, it's 5,000 newtons. So 5,000 newtons is the applied force of the engine. Now, what you're asked to do is look at 3 different cars and tell me which is the most powerful in terms of the force that it's able to apply from the engine onto the tires onto the road. Okay. And it allows us to move around. So forces are really important when we think about cars in general, but also really important when we think about Formula One racing. If any of you are interested in it, there's a lot of science and engineering that goes into making these cars work essentially. Now, it's not all about driving force. This is quite key. Okay, so you could have as much driving force as you want. You can have the most powerful engine, and it could mean absolutely nothing. So you could spin that, that engine could spin and spin and spin, push those wheels round and round and round and round. But if those wheels just spin on the ground, then that car's going nowhere. Okay, so what we need to do is we need to convert that driving force into another force. Okay, and this is where friction comes in. Friction, normal, and reaction forces are absolutely vital in Formula One, and that might seem a bit weird because surely you're thinking, surely you want to reduce friction and surely you want to reduce reaction forces. What I mean by reaction forces is your resistances. You want to reduce air resistance, but you actually need them. You need them to keep the car on the ground, and you need them to keep the car actually moving. So what we can see in this simulation, if you just watch, is that back tire. Look at it wobble. It's struggling for grip. And as it's struggling for grip, it's lacking friction. And this is causing this car to skid in a turn. And that can be quite dangerous. And it can cause the car to crash. And it could also cause the tire or the wheel to come off completely, which has happened in the past. So just watch the way it wobbles. And that's as the wheel is just trying to get grip on the road, because these tires are quite slippery in some respects if they aren't warmed up enough, which we're going to talk about in a minute. Now, the tires themselves, we'll talk about it now. Actually, the tires. Now, this simulation is a slow motion of a drag car, essentially. So they do drag car racing when they're really powerful cars that just go in a straight line as fast as they can, and then they use a parachute to slow them down. You can Google it or YouTube it if you want. Have a look. Look at the way that this tire, as the car's engine fires, look at the way this tire ripples and crumples under under the forces that are acting upon it. Now, this is obviously, and you wouldn't see this with your naked eye. You have to use slow motion to see this. But what you can see is that the ripples and the crumples in the tire are causing this car to start to move, and that's really key. Okay, so what's causing that is friction between the tire and the road. And if you didn't have that, then this car would go absolutely nowhere. Okay, so tires generally are designed to generate friction. We want friction between the road surface and the tire. Okay, but we only want so much. So this is a fine balance. If you have too little, then you're going to skid. And if you have too much, then you're going to have a loss of power. So here's the example of a skid here. So too much, again, the car goes sideways, and if it carries on going sideways, it's going to end up in a crash barrier. And you certainly don't want that to happen on the roads around the streets that we're driving around. You might end up crashing into a pedestrian or into another car. Now, Formula One cars, tyres, because they're what are known as slicks, they're very smooth surfaces. They need to be heated up. So you might have noticed in the past, Formula One cars doing this. They weave side to side to side to side when they're warming up. And what they're doing there is they're just increasing the heat within those tires so that they have a stickier surface, if you like. And what you can see in the middle simulation here is just the heat of those tires as it goes around a corner. So to start off purple, they're quite cold, relatively speaking, and as they go around that corner, that friction increases, and it heats up those tires, and it keeps that car stuck to the ground. So tires are really important, and they make use of friction between the tire and the road. So what we tend to find is if the car's moving in that direction, the applied force is in that direction. Friction is always in the opposite direction because it's a resistance force. Now, another thing that uses friction is brakes, and we understand hopefully that brakes are really important on any car or any bike, or being able to stop a moving object is really important. Now, brakes convert kinetic energy into thermal and sound energy, and they do that by friction. So what you have essentially is a circular plate and then two pads either side, a bit similar to if you think of like the brakes on a bike. You've got two pads that pinch, and they pinch the wheel, and they cause friction, and the kinetic energy is converted into sound and thermal energy. Very important in that sense. And what you can actually see on this left simulation is the heat that's generated in the brakes of the car. So they get extremely hot, and obviously they have a limit in terms of how long they're going to live. So it's pretty important. And you can talk about brakes and the use of forces. Again, friction is the force that's really important in this particular bit. Now, another use of forces in Formula One is the airfoil. So what I mean by this is the spoiler at the back. Now, the spoiler at the back is designed to push air upwards, which is a bit odd, isn't it? Why do we want to push air upwards? Now, the key thing here is this creates a downforce. So what we can actually see here is we can see the Formula One car, and we can see the air moving over it. Now, it's low to the ground. It's streamlined. It's good. That's all good. But what this bit at the back is all about is it pushes the air upwards, and as it pushes the air upwards, that creates a downforce. And what that does is it sticks the back of the car to the ground, and it stops that car from sliding around. It stops it from taking off. Okay, especially when you've got this airfoil at the front, you can actually generate a bit of lift, and you don't want lift on a Formula One car because this can happen. Although this isn't a Formula One car, this is Le Mans 24-hour endurance car. They're designed to be slippery, but this car just takes off. If you look, the front end lifts up, and the entire car just flips over. So something's gone wrong there. It's probably to do with some kind of turbulence coming from the car in front of it, and it's just caused that downforce to reduce, and it's just lifted that car off the road, which is pretty scary. If you look at it, imagine being inside that car. I think the person that was in that car obviously did survive, thankfully, and went on to carry on racing. Actually, I think it was Mark Webber. Anyway, that's a bit of knowledge. Now, the last bit we're going to look at is rocket science. So, rocket science is not rocket science. What I mean by that is it's not that hard actually to understand how a rocket takes off. Now, what we should be comfortable with is launching a rocket requires an applied force called thrust. Okay, so we call that essentially the force that pushes downwards, pushes that, that rocket upwards. And whenever you do this, you always get a reaction. So we know this. Every force has an equal opposite reaction. So overcoming these forces is kind of key. Now, when we talk about rockets, we're talking gravity and air resistance, generally speaking, at the start point, essentially. So we can see this here. Now, what this starts to get us thinking about at this point then is how much thrust do we actually require to lift a rocket off the ground and into the air. Now, we can use Newton's law again. Okay, so if we just take a rocket, a very small rocket, 1,000 kilograms, it's a ton still, but it's very small compared to some of the ones that we'll talk about when you look at in your assignment. Now, what we can do is we can work out the weight of a rocket. Okay, so its weight is going to be on Earth is going to be 1,000 kilograms multiplied by the acceleration due to gravity. So it has a weight of 98,000 newtons. Now, what that means is we therefore must give a thrust of greater than 98,000 newtons in order to overcome gravity. So what we need to do is we need to unbalance that rocket so that its force upwards is greater than the force downwards. So we're going to need, say, 99,000 newtons of thrust in order to lift that rocket up off the ground. Now, that might not be enough for us to get it going and accelerating and through the atmosphere, but it would at least get us off the ground as a starting point. So as you can see here, this simulation shows that thrust must be bigger than gravity, or the weight due to gravity. Okay, now rockets that you're going to look at have massive amounts of force that the engines can generate, and you can have a look at that. Now, SpaceX's Falcon makes use of two key fuels in order to do this. Okay, so we use liquid oxygen. Liquid oxygen is then mixed with a really refined, pure kerosene. So kerosene is a jet fuel. It's really, really reactive. It releases a lot of energy, and when we mix it with liquid nitrogen and ignite it, it releases a lot of energy and it creates a lot of thrust. Now, this actually gives this rocket thrust of up to 4,940 kilonewtons, or 4,940,000 newtons, okay, of upward thrust. Okay, now what you have to think about there then is, what's the mass of the rocket? So therefore, it's going to be less than the weight of the rocket is going to be less than that, and that gives it the acceleration required to lift off the ground. Now, this is all well and good. So we have to get up. Into the atmosphere. All right. Now, a rocket needs to speed up to at least, this is incredible if you think about this. In order to escape the Earth's gravitational pull, we need a rocket to speed up to about 17,800 miles per hour. And that's an incredible speed if you think about it. And it needs to fly above most of the atmosphere before it can turn off any of its thrusters and boosters. So you need enough fuel to get yourself from the ground to the atmosphere, and to get to that speed. So that's how much thrust we need, and that's kind of coming from that. And that just means that object doesn't get pulled back down to the ground. Okay, so we need that momentum. It's kind of a key word there. Now, once the rocket's up high enough, the air's really thin, so air resistance doesn't generally then play. It doesn't play a problem at this point. You're generally just fighting against gravity. And gravity gets weaker and weaker the further from the Earth you get. So that's kind of key. You just need enough momentum to keep yourself in orbit. Okay, cool. So that video basically covers all of the key information that you needed to go through the assignment worksheet for the merit and the distinction. If you have any questions at all, don't be afraid to give me a shout, and I can give you extra pointers. Okay, cheers.